Okay, let's just get started. So last lecture we discussed about why design verification is treated as a separate profession when IT engineers can really test their design through test benches. So we discussed that we are going to talk about 10 good reasons. So before we really discuss about those good reasons, let's just recap the case study that we discussed yesterday. So this is the requirement specifications for a single port memory. So basically we require a 32x8 single port memory, and it has to be a synchronous memory. This is the first requirement, and then the second requirement is that since a single port, so both read and write cannot be high simultaneously. And we discuss about the timing diagram, the write cycle and the read cycle, and then we discuss about how the RTL engineers actually describe the design in describe the design part in RTL, and then they write the test bench where they just instantiate the dot over here, and then actually drive the signals using the drive signals to test. Okay. Perform very similar as a write operation, write test or read test. So if we see the conceptual diagram of the test bench, so basically you have a design under test. So there's some nomenclature over here. So that is basically design under test. So this is let me just take out a different. Okay, so this is design under test, and basically it's also called this is also called design under verification. But typically it is called design under test. That, and then we have the driver part, which is actually generating these signals, and then we have a checker as well. So driver is basically driving stimulus, and what is stimulus? It's a set of signals to test a scenario. For example, you want to test a write memory transaction. So how these two are connected? So basically we have this dot over here, this one. So where you are initializing? This one here. This is basically the dot. All right, and then we have the driver part, this one. And where is this driver part? This one over here. And then so we are left with this checker. Driver is driving the signals, and then it is sending these signals to the checker as well, and getting the response from the dot as well to the checker. So let's say we want to we have written some data into an address at a memory location, and then we want to see whether data has been written properly or not. So we do a read transaction, and we generate another read transaction, and the same address is given, and then we get the data out as well. And we want to check whether the data has been written. We are reading what has been written. So we can see the dot, we can see the driver, but we don't know, I mean, what is checker. Okay, so basically checker is manually done up until now through waveforms. Okay, so you must have seen these waveforms. Okay, so this is what you have been doing so far. So now the 10 good reasons why for this design verification field. the first one, and this is really important actually. So you know the bigger picture first, and then you actually um, really know what is this field all about. Okay, so the first reason. Okay, so you can see the write operation over here. You are generating some signals, and then you're making the write. You're making the write is equal to 1 and read is equal to 0, and then you're specifying some addresses and then the data. And so these address and data values have to be swept to test all possible scenarios. So so if you're just testing only one or two tests, so you don't know what the behavior of the hardware when you will have different kind of addresses or data. So you need to have some sort of mechanism to generate some random tests for the address and for the data. So here's the solution is that we need to need random stimulus, or rather constrained random stimulus. We can do constraint that address has to be greater than a certain value or less than a certain value, or data has to be in this range. So you need to have some sort of a mechanism that help us to generate such a stimulus. So this is one of the reason. Then the second reason is checkers. So far, like I mentioned to you, so basically checking that whether your dot is performing as per the requirement or not. So you are doing this checking so far using the waveform, but this is not practical for complex SOC, and because there are so many signals and you just get lost, and then you need to the moment you perform any minor change in your design, then you have to reperform all these tests, and you have to do all these manually. So it's not practically possible. So the solution you need to have need automated checkers. Okay, so you need to figure out we need to see how we can write automated checkers. Okay, need to know how to write automated checkers. Okay, so these are the two reasons. First, you need to know how to write a generator signal, then you need to know how to write an automated checkers. And then the third important problem that we see these classical test bench scenarios, that signal manipulation is cumbersome for different scenarios. Let's say you are writing, let's say you are doing doing a write memory transaction, and you actually generate these signals at negative clock write is equal to 1, read is equal to 0, and address and given. And then for a different read after write, so you need to perform the write memory, you need to drive all these signals again, and then you have to drive a different set of signals for the read operation. Okay, and likewise you have let's say you want to test write, so multiple write and then read, so you want to check that whether you are getting the last write data. So you see that you have to manipulate all these signals again and again. So you need to have some high level abstraction to model this stimulus, and for like transaction support, like write memory or read memory. Okay, so you don't have to drive all the signals manually, just use some high level transaction for. So sorry for that. How do you do that? Okay, so this is what is we'll be talking about more in detail in layer test bench, higher level abstraction. But let me just give you a brief about what do we mean by this. So let's say you have this design under test over here in this layer 0, and then you have a driver. So this is so far what we have been doing in your test bench. Okay, so this is your design under test, and you have been actually using the driver to actually drive it. This is so far this typical test benching. So you're generating different clock read write signals for doing the transaction. This is layer 0 is a dot, and then layer 1 is layer 0 is your dot, and then layer 1 is your driver. Okay, and then what I want to suppose was talking about high level transaction. So you just go one layer up. So this is layer 2, where you have a sequencer. Okay, and what is the role of the sequencer? Is to generate these transactions. So generate these transactions. Okay, write memory or read memory, high level transaction. So you're just writing a write memory transaction. You just actually specifying what are you trying to specify here in the high level transaction for memory. So you just specify address and data. So you don't have to, and then for the read memory transaction, you just have to specify address. Okay, and then you will get a data from here. So this is just high level transaction that you have to specify, and then sequencer will generate these transactions, and it's the role of the driver to actually convert these transactions into low level signals. Okay, so we will be talking about this higher level abstraction layers to generate a layer test bench. I think we can stop over here, because otherwise the video length will be quite large. So what we have discussed so far, how many topics that we have discussed so far, for like, so one is you need to have a random stimulus support, and stimulus generation, then automated checkers, you need to know how to write them, and then you need to know how to drive signals using higher abstraction level. Okay, so far we have figured out 3 different main reasons to for this design verification field. So we still have 7 more to go, so stay tuned. We will talk about the remaining 7 in the next video. Thank you.